Okay, so this is the last portion, which is now we talked about temperature change when there's a volume change now. What about the pressure change? And this is all. And the short answer for that is once again, like this is a constant. Okay? And the definition of gamma naturally come out later. And we don't need to reinvent the wheel. You want to use the equation that we already know. V initial, temperature initial to the CVM over R, V final, temperature final, CVM over R. So that was an equation that just was defined from the adiabatic reversible expansion. So in this process, what I need to do, I'm not interested in temperature knowing about this. I want to know more about the pressure change, that is related to graphical demonstration of what are the work differences and which will be shown later. So what I need to do is I am going to this one. So I think the first let me just rewrite this way. I'd like to do it in the ratio. V initial, V final. R over C. I put down the ratio, and then I don't like this one to carry on, so I flip this so that the volume ratio in this term has a reverse power term, and this is my starting point. And then now I'm going to use my ideal gas law, which is temperature is pressure final, volume final. Divide by NR, but I am going to have the NR if you want to keep this way. And this is initial pressure, initial volume divided by NR, and this one goes away. So I'm just keeping these two terms as a rewritten form from temperature ratio. Okay? So I'm just essentially make my ways to get rid of this expression. Now all of a sudden, this expression contains only pressures and the volume. Okay? So then I have to put this one down. Okay, if I don't want any pressure, so I need to flip this one, and then that will be. Okay, so if I multiply both sides by initial, final volume, right? Do that. You start to see that becomes this plus 1, right? And that's Cp divided by Cm. Right? It start to come in this way. So Vi, Vn to the power of R CVM plus 1 is Pf and this one, when you say this one is same as CVM plus R. Okay? This is same as CV, CPM, CP. So then therefore, this equation now becomes pressure, volume to the gamma is constant. And the gamma is CPM, CPN plus R, CPN. Well, if somebody wants to write the other way, CPN minus R. Okay? Either way, it works the same, which is the heat capacity ratio on the constant volume. This is an equation I still remember after taking this class and not taking any other PChem class after all, but still this is an equation. It looks awfully similar to isothermal contrast. Remember, I wrote this one more time. This is an isothermal, which is happen to be the power of 1, right? This one now you have power of, for example, 5/3 for monoatomic ideal gas. If it is a diatomic ideal gas, it will be 7/5, right? In general, it could be a number, depending on the information was given. So depending on the types, the pressure drive is different. So once again, so now I'm going to draw, this is the final sort of drawing here to show it to you the meaning of this. And so here, okay, so this is an equation. So let me do this one in the 2 stages now. Okay, here, I'd like to draw, once again, my choice is volume versus pressure. Because you remember that minus P dV, that is the work reversible, right? So that's why I like to draw the P over V, and I can do the graph, and graph under the curve is the work. But now, what I'm doing now here is let me do the isothermal expansion. This is an isothermal expansion. Okay, and then I stop. So up to here, isothermal. And then what I'm going to do now is I want to switch to adiabatic expansion after that. Adiabatic. From here, I want to do the adiabatic expansion. And then what you need to have in your mind is, if I continue to have, this is an isothermal expansion, but my adiabatic expansion is something going lower. This is where I stop if I want to stop there. So that's the 2-stage process, isothermal, adiabatic. In this case, you need to provide a heat, right? Positive heat. It's to come. And this one is Q is 0. No heat is from the surrounding. So these are the 2-stage process, isothermal, reversible expansion, adiabatic expansion onto this. And then what are you going to do after that? Isothermal expansion. The same thing, if you do the isothermal compression, volume is decreasing this way, and then if you do the adiabatic compression, if you do the adiabatic compression, actually you are doing the work to the system. Work is positive, right? If the compression means work is positive, positive work means you're anticipating the delta T goes up. So you actually have a steeper rise, steeper change in the pressure versus volume. So this one completes the cycle, if you think about it, right? So that is what is called the Carnot cycle in chapter 3. These almost start with the Carnot cycle right in the beginning on the second law of thermodynamics. And we already have that information, okay? Isothermal, milder change in the pressure drop, steeper rise in the pressure drop in the adiabatic, and then milder increase, isothermal, and adiabatic, that's compression, more steeper rise in the pressure of the compression. So that completes this 4-stage process, what we call the Carnot cycle. this one is, this is an expansion of the compression. The compression means is actually heat has to leave, so heat is a negative. If you think about it, I'm compressing the gas. Compressing means work is positive, positive work. Delta you're supposed to go up, but you maintain to be constant. What that means is you need to take out the heat. Okay? You're supposed, when this one is work is positive here, right? This is work is negative here. Yeah, so that's all the consequences, the opposing sign of this. So in this case, is your heat is coming in. Right? So this case, your heat has to come out from the system upon the compression here. And then you have a 0Q is here. So this one is a complete description. And the area on here is, we call this way, that is your work of a cycle. I'm already covering the chapter 3 now. Okay? But this is, I'm going to go back and tell you again one more time. But this, the region that we talk about pressure change in isothermal versus adiabatic in this form, it's just a way to restart to the Carnot cycle. This Carnot cycle, the person Carnot was not a well-respected scientist. He's just a very, I guess he was one of the cadets and who had the thesis that he wrote it, and he wrote a book. And then, I mean, in those days, you wrote only like 20 copies of the books. He submitted, and I guess he got his degree, and he disappeared, I guess, right? And then later, somebody, I think the Lord Kelvin, find out his consideration of this 4-stage process on the Carnot cycle is actually very important. Give a rise to the concept about entropy, which is I'm not going to talk about the definition now here, but its concept can be easily explained here, and then that's became essential part. Entropy is an essential part about G, right? Gives free energy. Thermodynamics, chemical thermodynamics is all about G. It's all about G. Whether it's a systems perspective, the change is spontaneous or not, we have a very important handle, and then you gotta know about entropy change, and this is actually coming from history. Okay, we have a little bit